Hello and welcome again for another EE324 video. In this video we'll be discussing linear systems of ODEs. I'm going to note here that I'm writing x dot, which is a notation that you may or may not have seen before. X dot just means the derivative of x with respect to t, so dx dt. And the i's here just represent individual differential equations. So we'll have n of them in this case, because now we're dealing in systems of ODEs rather than just a single ODE. And you can see that we can write that out. So we have the first ODE written here, and the second ODE written here, and so on all the way to the nth ODE. And there is some relationship between the ODEs. That's why it's a system, right? So we have here, like in the first ODE, we have something that's a term that's related to the second ODE and the nth ODE over here, and so on. And then we also have an external kind of input that could be given to each of the individual ODEs, this function f here. If the system is written as it is above, it's said to be in normal form. Not something that we're going to need much for this course, but just as a reminder, we're gonna see that everything should be written in normal form, and that's generally how you'll get it anyways. Another thing to note is if let me get my pen here. If all of the f's, so each one of these f1, f2, all the way to fn, this is what this says: fi of t is equal to 0 for all I. This means for all. That's the symbol for all. So if every I, f of t is equal to 0, so f1 is 0, f2 is 0, fn is 0, all the way to fn is 0, then the system is said to be homogeneous. So this is just like before. We're going to have homogeneous and non-homogeneous cases, except for, in this case, if even a single one of those differential equations has a term, a function of t, that is non-zero, then the system is said to be non-homogeneous. Okay? So that's going to be a key difference here. The system, we can write this system above in a nice abbreviated format in matrix form, which is the vector x dot is equal to a times x, where a is the matrix and x is obviously still the vector, plus f. Okay, so in this case, the x prime here, we could have written it as x dot, but we'll write it as x prime, is typically a derivative with respect to time. So we usually start thinking about these things as being in terms of the independent variable being time. And just to reiterate what was said up here, if f is equal to the 0 vector, which means all of the entries of that vector are 0, all n of them, then we can write this system up here that we have up here. Obviously, if f is 0, it just goes away, and we can just write it like this. So this one, if you see something written in terms of this without an f vector on the end, that means that it's a homogeneous linear system. Okay. At least what we'll be dealing with will be homogeneous linear systems. And for the rest of the video, we're mostly going to deal with homogeneous ones, but I am going to show an example in a moment of a non-homogeneous one, just so that you get an idea. But most of the rest of the video will just deal in homogeneous linear systems. So as an example, suppose we have this following system: x dot is equal to 2x plus 3y, and y dot is equal to 3x minus 5y. Okay, Then our vector x, we're going to write that as xy. And our A matrix is going to be 2, 3, 3 minus 5. And our F matrix, notice there's no functions added on other than the x and the y, so our F matrix is just going to be 0, 0. So this is an example of a homogeneous system. So we could just write x dot, or x prime, is equal to A times x. And obviously x here is just that vector x, y stacked on each other. And then this one will just be the derivative of each of the individual terms, right, in the vector with respect to time. Now let's get an example with a homogeneous one. Suppose we have the following system. X dot is equal to 6x plus 2y minus z. And we have y dot is equal to 3x minus 7y plus 2z plus 10t. And z dot is equal to x minus 2y plus 3z plus 2t. Then we can obviously write x. Our x vector is just going to be x, y, z. We're going to have A, which is going to be a 3 by 3 matrix. It's going to be 6, 2, minus 1, 3, minus 7, 2, 1, minus 2, 3. And F is not going to be 0, the whole 0 vector in this case. There is a 0 term here. There's no t, no function of t up there. But 0, 10, and 2 would be our function f times, I guess I should have my t's in there. Okay, or I could have had it as plus f times t. Either one would work, right? I could have plus f times t, or just include the t inside of f, whichever is more convenient. Okay, so this is an example of how we could write these systems. And then obviously this would just be, again, x dot is equal to ax plus f. We need that plus f now. So we're dealing with linear systems for a reason, because in the case of what we're going to be interested in is the solution. We're going to want to find x, right? Which is the solution. We call this the solution vector. So we're going to want to find the solution vector, also called this is also called the trajectory. And then the n-dimensional plane, because this is going to be a vector. This is going to be a vector in n by 1, right? So it's in n dimensions. The n-dimensional plane that x is in is called the phase plane. So you might hear me use this term, phase plane, when discussing these systems of differential equations. It turns out that for a linear system, the solution is unique so long as the functions are continuous on a common interval. So we're going to be dealing with mostly functions that obey this. So for the most part, you're going to be able to just assume that that's true, and we won't bother with worrying about it. But it's something that you should know. A lot of these things, everything has underlying assumptions, which is sort of the idea I've been trying to build into the course. Now, you should remember that we had something called the superposition principle before. That's going to come back. And in this case, for homogeneous systems, we should have n unique solutions, where n is the size of that vector, right? And each of them is going to be x1, x2. These are all going to be solutions, right? x2 ... xn. Just like before, we saw something similar. But in this case now, these are vectors. And the superposition principle, as you should remember, says that if I have each of these n solutions, then another solution could be this. C1 times x1 plus C2 times x2 plus ... Cn times xn. So basically, this is the superposition, and the assumption here, of course, is that these are linear ODEs, linear coupled ODEs in n linear coupled ODEs, right? So the general solution then is just going to be some superposition of each of the n individual solutions. And then in the non-homogeneous case, just like before, we're going to have a complementary solution, which is the solution, remember, where this would be equal to the vector f would be equal to the 0 vector, right? So we would be able to solve it that way. And then we're going to have a particular solution, and the general solution is a superposition of those. Again, non-homogeneous, linear. I should make sure that I write that in there. And let me see, I'm going to erase this. And the particular, the general is x equal to xc plus xp. Okay, and we're not going to, as I mentioned, we're not going to really deal in this video with the non-homogeneous case very much, but we should be aware that it's there because it may show up later in the course. Here's an interesting fact. A solution in the homogeneous case of the system x prime equal to ax may be written as follows. x is equal to some vector, say k1 of I, k2 of I, dot dot dot, kn of I, where I is the ith solution, right? So we're going to have n of them in this case, right? We know that. So the ith solution, e to the lambda I t, which I'll tell you what that is in a minute. So we could write it then as the vector ki times e to the lambda I times t. And it turns out that we can actually tell you what each of these things are. Ki is the ith eigenvector of A, and lambda I is the ith eigenvalue of the matrix A. Okay? So basically we can write the solution out as follows. The full solution, this should have been xi, by the way. The full solution is going to be equal to c1 k1 e to the lambda 1 times t plus c2 k2 e to the lambda 2 times t plus dot 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 plus kn e to the lambda n times t. So all that we have to do to find the solution of a linear system of ODEs in the homogeneous case is we just have to figure out what this matrix A is, find its eigenvalues and eigenvectors, and that will give us our solution. It's sort of an amazing property. This is true, by the way, I should mention, and if the eigenvalues are all unique. So if all of the eigenvalues are unique, so lambda 1 is not equal to lambda 2, which is not equal to lambda 3, and so on, none of them are equal to each other, then there's no pairs that are equal to each other, then we can write the general solution in this way. What happens if they are not distinct? Okay, so if they're not distinct, then we can split into two cases. One, the first case is that the eigenvectors for the non-unique eigenvalues are unique. So I'm going to reiterate this. So even though there might be 2 eigenvalues or 3 eigenvalues or whatever that are all the same value, the eigenvectors corresponding to those eigenvalues are unique. So maybe if you had, say, your second eigenvalue and your third eigenvalue are equal to 2 as an example, if that's the case, but each of those 2 eigenvalues has a different eigenvector. In that case, it looks very much similar to the case above. Then x is going to be equal to c1 k 1 e to the lambda 1 t. I'm just going to, by the way, eigenvalues we don't, they don't necessarily come in any particular order. So I'm just going to reorder all of the eigenvalues and assume that, say, lambda 1 is the one that has multiple eigenvalues. And you could have the case where you have multiple pairs or triplets or whatever. Like you could have in a 6D system, you could have 3 eigenvalues be equal to 1 and 2 eigenvalues equal to 2 and 1 eigenvalue equal to -1 or something like that. So you can have that kind of a scenario. But then I'm assuming that the non-unique one right now is lambda 1. So then it's going to be k2 times e to the lambda 1 t plus dot 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 plus c I'm going to write this solution as corresponding to lambda 1. Okay, so we have m of these that are the same. Km e to the lambda 1 times t, lambda 1 times t, and then basically the general solution is just x is equal to c1 k1 e to the lambda 1 t plus c2 k2 e to the lambda 1 t plus dot 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 plus cm plus 1 km plus 1 e to the lambda 2t plus dot 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 all the way up to obviously kn e to the lambda. I'm going to assume there's k unique eigenvalues. E to the lambda kt. Okay, so that would be our general solution. So it doesn't look very different from this other than the fact that instead of lambda 1, lambda 2, and so on, you have multiple lambda 1s, for instance. But we can have a case where the other case, which is the eigenvectors are not unique, the eigenvectors, not the eigenvalues, right? So this is the case of non-distinct eigenvalues, so that means the eigenvalues are not unique and the eigenvectors are also not unique. Then the solution will look more like something interesting. We will have something that looks like this. x1 is equal to k11 e to the lambda 1 t. x2 is equal to k21 e to the lambda 1 t. Sorry, k21 times t e to the lambda 1 t plus k22 e to the lambda 1 t. And if we had to keep going beyond that, we're only going to be generally dealing with 2 and 3D systems, but as we go higher, this could become more prominent. I mean, I guess in a 3D system, you could get something that looks like this too. We could have k31 t squared e to the lambda 1 t plus k 3, 2 e to the lambda 1, t e to the lambda 1 t plus k 3, 3 e to the lambda 1 t. And then we can just keep going until we get to however many we need. So the mth one, which is just going to be km1 t to the m minus 1. Oh, I forgot over 2. I forgot my over 2 here. Over m minus 1 factorial e to the lambda 1t plus k m 2 t to the m minus 2 over m minus 2 factorial e to the lambda 1 t all the way down to obviously k plus k m e to the lambda 1 t. Okay? And then our solution is going to be, our solution would then have to be x is equal to x1 plus x2 plus dot 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 xm, right? So we have m solutions now, plus dot 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 all the way up to xn. So these first m are going to be these solutions that we saw up here, which have t's in them, right? Have powers of t in them. That's how we would get to our solution. Now, this assumes that we have m non-unique eigenvectors. So you could have very strange situations that we'll probably not run across very often, but you could have a situation where you, say, have an eigenvalue that repeats or has the terminology has multiplicity, say 3, but the eigenvector, there are 2 unique eigenvectors and one of the other ones is not unique. In other words, it matches with one of those 2. So in that case, you would have just 2, you would have 3 eigenvectors, but only 2 of them, so you would only end up having to go to power t here in that scenario, instead of going up to t squared, because the problem is really how many unique eigenvectors you have is what determines the power of t here. Or actually, I should say that the other way around. How many non-unique eigenvectors you have determines this. Okay, so I've said a lot, but this probably doesn't help too much figure out actually how we go about computing these things. So let's go into some examples. Let's say we have x dot is equal to x plus 2y, and y dot is equal to 4x plus 3y. That means my x is going to be equal to just xy, and my a is going to be equal to 1, 2, 4, 3. And of course, it's homogeneous because I could write it as x dot is equal to ax, right? So it's homogeneous. And there are ways to deal with non-homogeneous ones. But we're not going to see much of that because there's actually some interesting cases here that we are going to be dealing with. We're going to obviously have the case of unique eigenvalues. We're going to have the case of non-unique eigenvalues, and then we're also going to have the case where we have at least some of the eigenvalues are complex. So it turns out, by the way, that you can, if all of the entries of A are real numbers, then you can only have complex conjugate pairs of imaginary eigenvalues if you ever run into complex eigenvalues. But that's not the case in general. If these are imaginary numbers, then you could have any number of imaginary solutions. Something to keep in mind. But we're going to be dealing with real numbers, so let's not dwell on that for too long. So what do we have to do? Well, step 1 is find the eigenvalues. And eigenvectors. So to find the eigenvalues and eigenvectors, well, the first thing is remember that if we want to find eigenvalues, we had this fun equation here, a minus lambda I times some vector v equal to 0 is what we're looking for. And if we want to find the eigenvalues, we need to find the determinant of a minus lambda I and set it equal to 0. We saw that in a previous video, so basically I would say determinant of a minus lambda I must be equal to 0. Okay, so let's look at this. We have the matrix a minus lambda I is equal to the following matrix. It's going to be 1 minus lambda, 2, 4, and 3 minus lambda. Right? So then the determinant of that is equal to 1 minus lambda, right, because I'm going to do this crossing here. 1 minus lambda times 3 minus lambda minus 2 times 4. And using this fact, we're also going to say that has to be equal to 0. Right, so then we can multiply this out, and you can check that I multiplied everything out right, but I end up with lambda squared minus 4 lambda minus 5 equal to 0. So you have to multiply this out and then subtract off 8, right, because this is minus 8, and you get to this as my answer, and then we can factor this to find the eigenvalues. So lambda minus 5 times lambda plus 1 is equal to 0. So that means that I'm going to call, say, lambda 1, I'm going to call that 5, and lambda 2 I'm going to call negative 1. It doesn't really matter. We can order these however we want. You could order them from low to high or whatever. So now we found the eigenvalues, and they're two unique eigenvalues. So we know that we're going to have the case that we saw way up here of unique eigenvalues. And so now we have to find the eigenvectors. And that just directly comes from this equation. Our ith eigenvector is solving this equation. So basically I'm going to say, okay, I'm going to have a minus lambda 1I times v1I. This will give me, v1. And this will give me equal to 0. The zero vector will give me my v1th eigenvector, my first eigenvector. So then lambda 1 was 5, so this is going to be a minus 5I times v1 is equal to v1 vector. I'm going to distinguish between vectors and components here in a minute. So that means that the original matrix A was this matrix, 1, 2, 4, 3. So it's going to be 1 minus 5, 2, 4, and then 3 minus 5 times my vector. I'm gonna have two components to this vector. It's going to be equal to the vector 0. Okay, and obviously this becomes negative 4, 2, 4, negative 2, v1, v2 is equal to 0, 0. Now often what we're going to find is that we're going to have a free variable to help us figure out the vector, the eigenvector. So how we could do that is we could say, okay, let's actually multiply this out. This says minus 4v1 plus 2v2 is equal to 0. That's the top part of this. And then we're also going to have another equation that says 4v1 minus 2v2 is equal to 0. Now notice that this equation is just the negative of the top equation. So they're the same equation. They're telling us the same thing. So we only have to actually solve one of them. And what we're going to find is, so we're going to get a free variable, a slack variable. We're going to find that 2v2 is equal to 4v1, which means that v2 is equal to 2 times v1. So if we let's let v1 equal to 1, then our eigenvector will be, we don't want it to be 0, by the way. We're looking for an eigenvector that's not zeros. v1, the vector, will be equal to, I let v1, the first term, be 1, and v2 is equal to 2 times v1, so that means this is going to be 2. And this is associated with eigenvalue with the eigenvalue 5. Now I have to do the same thing for the other eigenvalue. So the other eigenvalue was 1, I believe, minus 1, sorry, was minus 1. So we have to do 1 minus negative 1. Uh, 2, 4, and 3 minus negative 1. Which is equal to 2, 2, 4, 4. And then we know that we're going to have 2, 2, 4, 4 times v1, v2 is equal to 0, 0. Okay, and this just tells me that 2v1 plus 2v2 is equal to 0. And the bottom one is just a multiple of 2 times this. So again, we have a free variable. We're going to end up with a free variable that we can choose some convenient thing. So this means that v1 is equal to negative v2. So again, we'll let v1 equal to 1. That means that the vector v2 is equal to 1 minus 1. Okay? And associated with eigenvalue negative 1. So what that means is that our solution, thus, our solution is x is equal to c1, and what was the vector? 1, 2. So times the vector 1, 2, times e to the 5t plus c2 times 1, negative 1, e to the negative t. That's our solution. Okay. Let's do another example. We should be able to roll now. We have x dot equal to 3x minus y, y dot equal to 9x minus 3y. So again, we're going to choose x equal to xy. A is equal to 3 minus 1, 9 minus 3. X prime is equal to a times x. And we need to find the determinant, right? So now we need to find eigenvalues and eigenvectors. So I need to get the determinant of 3 minus lambda minus 1, 9, 3 minus lambda. And I'm going to set that equal to 0. And then I get, which implies that 3 minus lambda times 3 minus lambda minus negative 9 is equal to 0. And if you solve this all out, you find that lambda 1 equal to lambda 2 equal to 0. Non-unique eigenvalues. So the question is, are the eigenvectors unique? So let's find out. So basically, again, we're going to have a minus lambda 1 times I times v1 equal to the 0 vector. So this tells me that I have 3 minus 0 minus 1, 9 minus 3 minus 0. Oh, I think I messed this up. This was minus 3. This should have been minus 3 up here. And this should have been minus 3. Okay, sorry. I got my minuses back in there. And that's how we got the equal to 0. Okay, so then this is just, obviously, this doesn't change anything. It's just the same as the original matrix. And now we can try to find the eigenvector, or we will find the eigenvector. So what we get is the following. We get v1, v2 equal to 0, 0. And what does this tell us? This tells us, well, that we have 3 times v1 minus v2 equal to 0. And we also have 9 times v1 minus 3 times v2 is equal to 0. And notice that these are multiples of each other. So that gives us one free variable. What that means is that if we had gotten two free variables, so if, let's say we had gotten an equation like v1 minus v1 equal to 0 or something like that. So you get 0 equal to 0. Then you would have two free variables. You'd be able to pick either one. And so you would be able to, then you would be able to find two unique vectors. But in this case, we only have one free variable, so we're only going to be able to pick one vector. And this equation tells us that 3v1 is equal to v2, or v1 is equal to 1/3 v2. Right? And so we could say let v2 equal to 1, then we would get 1/3 1 as our vector. Right? So now, because we only have one free variable, there's only one vector that goes with this. And we need two vectors. So now that means that we're going to have to find a second vector so the eigenvectors are not unique. So now how we can find the next vector is we can go through and look at our, there's a method called the generalized eigenvectors. So we know we need another eigenvector, and we're going to have to go find it using generalized eigenvectors. So the idea there is that we have a minus lambda 1 I times v1. We already have that vector. Sorry, v2. We don't have that vector, but we do have v1. So we're going to solve this equation. So now we can solve this equation. Simple enough. And basically what it says is, again, we have the eigenvalue is 0, so we go 3 minus 1, 9 minus 3 times v1, v2 is equal to, well, what was our first eigenvector? 1/3 1. Okay? So this tells us 3v1 minus v2 is equal to 1/3, and 9v1 minus 3v2 is equal to 1. Okay, and then we get something like 3v1 minus 1/3 is equal to v2, and we could just say let v2 equal to 1. So that means my vector v2 is equal to 1 down here, and I believe this gives me 4/9 up here. Okay. Okay, so now the question is, what is the final solution? What we're going to note is that e to the 0t is equal to 1. okay, because obviously our eigenvector is 0. So that means our solution is x is equal to c1 times 1/3 1, that vector, plus now we need c2 times 1/3 1t plus c2, they're going to inherit the same constant there, times 4/9 1, this vector. So that's my general solution. Notice I have the t there. Okay. We could also have other situations, so let's look at that. I'm going to write this out real quick. X dot equal to 3x minus y minus z. Y dot equal to x plus y minus z. Z dot equal to x minus y plus z. So that means my x is equal to x, y, z. My a is equal to 3 minus 1 minus 1, 1, 1 minus 1, 1 minus 1, 1. And again, it's homogeneous, right? So we could write this whole equation. There's no f of t, no function of t on the end. So now to find the eigenvalues, eigenvals, we have to take the determinant of a 3×3 matrix. Minus 1, minus 1, 1, 1 minus lambda, minus 1, 1 minus 1, 1 minus lambda. Oops, I forgot. This is a matrix, and then I'm finding the determinant of this. This is going to be equal to something like, okay, so basically the idea to find the determinant of a 3D matrix is you take this and multiply it times the determinant of this. So take this, multiply it times that determinant, and then this one would be times the determinant of anything not including the row. So you would cross out these terms here. Those terms would go away. So I would go like this and multiply times the determinant of 1, 1, minus 1, 1 minus lambda, and so on. So I'm going to actually write out the terms here. So it's actually 3 minus lambda times the determinant of 1 minus lambda minus 1 minus 1, 1 minus lambda. And you should minus times minus, I'm going to actually let you compute this because you can do the 2D determinants, minus -1 times the determinant of 1, 1 minus 1, 1 minus lambda. And then this one is going to be plus -1 times the determinant of, well, I'm going to cross out this row here. So it's going to be 1, 1, 1 minus lambda minus 1. Okay? And this should, if you do this all outright and you do all of the multiplication, this ends up being negative lambda cubed plus 5 lambda squared minus 8 lambda plus 4 is equal to 0. All right, because we're looking for the eigenvalues, so we set this equal to 0. And if you do this actually by inspection, lambda equal to 1 works. right? So if I plug in 1 here, that gives me 0. And then we can figure out what the other eigenvalues are by use long division to find the others. So basically we would divide out lambda minus 1 into this minus lambda cubed plus 5 lambda squared minus 8 lambda plus 4. So I would find, okay, minus lambda squared multiplies this, so I end up with minus lambda cubed plus lambda squared. And if I do that, then I get 4 lambda squared minus 8 lambda plus 4 is left over, which means that I have to multiply this by 4 lambda. And that gives me, I'm going to be subtracting this off, 4 lambda squared minus 4 lambda, which leaves me with minus 4 lambda plus 4, which then means minus 4 up here. And then if I do the minus 4, it becomes minus 4 lambda plus 4. So that gives me a remainder of 0. So that tells me that lambda minus 1, for instance, was actually a factor. And then I can factor this, which gives me lambda minus 2 times lambda minus 2. So that means lambda 1 is equal to 1, and lambda 2 and lambda 3 are equal to 2. Okay? And so in this case, what that means is that I have non-unique eigenvalues. I will let you should solve out the first case for the first eigenvector. And what you should find is that if you let v1 equal to 1, then you get two equations that say v1 equal to v2 and v1 equal to v3, which implies that v1, the vector, is equal to 1, 1, 1. If you were to choose v1 equal to something else, you might get something else, which is fine, but if you want to verify that you're correct, do it this way. Okay? Then v2 we get I'm going to let you again solve everything out, but we get equations v1 minus v2 minus v3 equal to 0 3 times. Why is this important? So we get v1 minus v2. These are my three equations. This is important because we get two free variables. which means we can make two different vectors. So this is not the case of non-unique vectors. This is the case of unique vectors. And so, if I say, okay, so let, by the way, this equation, this says v1 is equal to v2 plus v3. So if we let v2 equal to 0, v3 equal to 1, then the first vector, so we'll call that v2, is equal to 1, 0, 1, right? Because 0 plus 1 is 1, so that gives me my v1. We could also choose v2 equal to -1 and say v3 equal to 1. So that would give me another vector, v3. This is why it's important, because we have a choice of variables, so we can pick two different ones, which means that now we can actually make two unique vectors with these equations. This would give me 0, -1, 1. Okay, so then my solution in this case is going to be C1 times 1, 1, 1 e to the t, because that was the first one. And this one's going to be C2 times 1, 0, 1 e to the 2t, and then this is going to be C3 times 0 minus 1, 1, and also e to the 2t. Okay, so in that case we didn't need to go up in dimensions. Hold on one second. And so this is our solution that we get. So let's do another example. I'm going to switch to a different color now. Let's say we have dx dt. This is just x dot, right? It doesn't matter. 6x minus y, and dy dt is equal to 5x plus 2y. Then we get x is equal to xy, a is equal to 6 minus 1, 5, 2, and x prime is equal to ax. Okay, so again, we're going to do our whole, we need to do the eigenvalues, so we find 6 minus lambda, minus 1, 5, 2 minus lambda, and this should give me the following if you multiply everything out and add everything correctly. I'm going to let you do the determinant in other words. Equal to 0. And we could easily find lambda using the quadratic equation, right? 8 plus or minus, we get 64 minus 4 times 1 times 17, all under the square root there, 2 times 1. We get a minus 4, so under the square root sign if we do this, which is equal to 4 plus or minus 2 times I over, sorry, just this. This is my answer for my lambdas, where I is equal to, of course, the square root of -1. Okay, so it's an imaginary number. Now we have complex. Notice that we got a complex conjugate pair, and again, I told you earlier on that we would find something like that. So when we're going through and finding the eigenvectors, we're gonna have to actually do this. A minus lambda I. Well, let's say lambda 1. Let's call lambda 1 4 plus I, and lambda 2 4 minus I. Okay, so A minus lambda 1 times I is equal to 6 minus 4 plus I, but I need this all in parentheses, right? Minus 1, 5, 2 minus 4 plus I. And that means that this matrix is 2 minus I, because 6 minus 4, the real parts here, can be added together. So 6 minus 4 is 2. Then we get minus 1, and we get 5, and we get minus 2 minus I. And then obviously we can come down here, and then we say, okay, so we have 2 minus I, minus 1, 5, minus 2 minus I, times v1, v2 is equal to 0, 0. And 2 minus I times v1 minus v2 is equal to 0. And prove to yourself that the following this gives 5v1 minus 5v1 equal to 0, or 0 equal to 0, when substituting in this thing. So this one just tells me that v2 is equal to 2 minus I v1. So when substituting in v2 equal to 2 minus I times v1. So I want you to actually multiply this out. I'm going to say let v2 equal to 1, because that's going to make my life easier. This implies that v1 is equal to 1 over 2 minus I. And if I multiply by 2 plus I over 2 plus I, so let's do 1 over 2 minus I times 2 plus I over 2 plus I, right? I'm multiplying by 1. I get 2 plus I divided by 2 times 2, which is 4, minus 2I plus 2I, so that goes to 0, so I don't get anything with I in it. And then I get minus I times I, which is minus I squared, but I squared is negative 1, so I get plus 1, so this becomes over 5. Okay? So this means this is the same thing as 2 plus I divided by 5. So that means my first vector is 2 plus I over 5 and 1. And I want you to prove again to yourself that this gives me 0 equals 0 down here, which is a nice slack variable. Solving for V2, it's a very similar process to what we had before. You should find, I'm going to let you follow through on the details, but 2 plus I minus 1, 5 minus 2 plus I times V1, V2 is equal to 0, 0, which gives me 2 plus I times V1 minus V2 equal to 0, and 5V1 plus negative 2 plus I V2 is equal to 0, and this implies that V2 is equal to 2 plus I V1. So again, we can let V2 equal to 1, which implies that V1 is actually going to be equal to 2 plus I over 5. So the other one was 2 minus I over 5. So then our V2 is just 2 minus I over 5, 1. And our solution is x equal to C1 which eigenvalue was this one? Minus 4, so 4 plus I. So this was the 4 plus I. So 2 plus I over 5 over 1 e to the 4 plus I times t plus C2 2 minus I over 5 1 e to the 4 minus I times t. That is our solution. And this can be written in terms of sine and cosine. But we're not going to do that right now, because we'll learn about that later as needed. Okay, but we could have written this in terms of sines and cosines. So you would get e to the 4t times cosine of t minus sine of t, I think, something like that, somewhere in there, over here, and so on. Okay? So we'll learn about that as we need. So the last thing that I wanted to discuss is the phase space examples. For example, unique negative real eigenvalues. So what would that look like? Something like this. It doesn't look exactly like this, but it would look something like this. Where no matter where you start in the phase plane, no matter where you start for x1, we could have this as x1 and x2. No matter where you start, you end up at 0, 0. Okay? This is for homogeneous systems. Okay, so this would be an example when you have unique negative real eigenvalues. You can have a case where you have like one positive, one negative. So you might have, let's say this one is positive, so that means that it's always trying to go away from the thing, and this one is coming in. So that means that something might come in real close. It might come in real close and then go up like this. Come in real close and go up like this. Come in real close and go down like this. Right, so one of the dimensions is trying to push you towards it. Oops. And the other dimension is trying to push you away. So this is, 2D phase space. I should have written that. These are 2D examples. So one of them is trying to push you towards, the other is away. So this is one negative real, one positive real. Eigenvalue. You could have complex conjugate pair. So if the real part is negative, then we would have something that looks like this. Say you start up here, you're going to go around and come down to here. So you're going to kind of spiral inwards. If the real part is negative, complex conjugate pair, real part positive, you're going to get something like this. Except for it's going to go the other way. It's going to spiral outward. Okay. And then if you had something like non-unique, but say both negative, it's going to look similar to this. It's just going to have something called transients. So it might actually grow away from zero for a short time and then go back to it. But the end story looks like this. Okay, if they were two negative reals, and if you had one real, one positive and one negative, it would look similar to this story as well, just with the transients. So it's not going to just immediately close in on in one direction or whatnot. Okay, so those are the examples in 2D of different situations that we can have. So why is this important? If you know what the eigenvalues are of the system, you can tell things about, for instance, the stability. So the stability of the system is related to the eigenvalues. What do I mean? I should say of the system's fixed point. and I should put that this is also a linear system, right? But the stability of a linear system's fixed point is related to those eigenvalues. Okay, so notice that in this case we could always shift the fixed point. In this case, the fixed point is at 0, 0. It could be shifted. We could translate it around or whatnot. But the analysis just looks the same. It's just that now you've moved from 0, 0 to some other point. Okay. But the stability of that fixed point is related to this, and it's only stable. This is the stable case. If the real part of the eigenvalues is negative. Why do I say the real part? Because notice here that also we close in on that fixed point, right? So, and that was the case where we had a real part that is negative. Up here, the eigenvalues were real, so the real parts are of course negative. So in these two scenarios, the fixed point there, the 0, 0 fixed point, which again could be translated around, it could be 1, 2 or whatever, but will be stable. In the other cases, even if it's a mixed stability, right? We saw the example here of a mixed case. Notice that it doesn't converge to the 0, 0 point in this case, right? I come up and I get closer and closer for a while, and then I go right away because this part is telling me, the unstable part is telling me to move away from the fixed point. Okay, so the only two cases are when all of the real parts of the eigenvalues are negative. And that extends into higher dimensions. So if it's 10D, then you need all 10 of the eigenvalues to be negative. Okay, so that's all that I have for this video. I hope to see you again soon.